Hello everyone, welcome to our final lecture for this course, 5.4 Working with Taylor series. Okay, it's amazing. It's an amazing feeling that we've journeyed through this course and we've reached the final step. So thank you for walking this journey with me. Let's begin the lecture. We start with the binomial series. If you had taken statistics class before, you would have come across this. And you can see that its basis actually also comes from calculus. And so it's very interconnected, probability and calculus. And so we're going to see how Maclaurin series actually, for a particular function, is the binomial series. So when you write your Maclaurin series as f of x, or rather when you write the Maclaurin series for f of x equals 1 plus x power r, you get the binomial series. And the binomial series is an expansion, okay, that comes from 1 plus x power r. And we use a special notation, as you can see. You see that it's showing r and n up and down, right, with that notation. The more popular notation is NCR, because your calculator also has that function under the probability keys. So NCR is the notation, but RN, that way we write, is also utilized in many books. Well, they are all equivalent expressions. NCR is a nutshell to say it's r factorial over n factorial times n minus r factorial. And when you write the series f of x, the series for it, you put the summation, of course, and 0 to r NCR x power n. So that's the binomial series idea, okay, 0 to r. Now we want to give a formal definition, because when we say Maclaurin series, we want to make sure that the series is included for all for n 0 to infinity. Okay, so we say that for any real number, the Maclaurin series for f of x is the binomial series, and it converges to f for absolute value of x less than 1, and we write it like this. Okay, so we have 1 plus x power r is summation 0 n 0 to infinity NCR x power n. And then I kind of expanded it for you here. So that is what we have as the definition. Okay, we'll do problems so that you can begin to follow along more clearly. Find the binomial series for f of x equals square root of 1 plus x. If we explore this problem, we can see that f of x, which is square root of 1 plus x, can be written as 1 plus x power half, right? Therefore, if you compare this with the Maclaurin series for 1 plus x power r, you can see that r here is a half. So then you could use the series, the binomial series, which is n 0 to infinity half n x power n. Okay. Because you had it as, let's just write that by the side. The general form was r n x power n, right? In the place of r, we now have half. And let's also expand this. They get 1 plus half x, half times half minus 1 over 2 factorial x squared, plus half times half minus 1 times half minus 2 over 3 factorial x cubed, and so on, right? Let's see if we can write a general version for this. So 1 plus half x, that comes out to be a minus, because you have a minus half times half. So I'm trying to write it as 1 over 2 factorial, let's bring the 2 factorial out first, times 1 over 2 squared, right? Half times half. The negative, you get half times the negative half, but the negative is pulled out here. So it's half times half, so it's half squared, or 1 over 2 squared, x squared plus, we'll bring the 1 over 3 factorial out here. That's a half times negative half times negative 3 over 2, right? So then let's write that as 1 times 3 over 2 cubed x cubed. If you expand this, you'll get this, okay? So you have, I'm going to erase this after I show this. This is half times negative half times negative 3 over 2. So you have 3 of the 2's in the bottom, right? So that's 2 cubed. And then you have negative times negative, which makes it positive, and 1 times 3 on the top. Okay. All right. And the next term would be a minus, right? And then now if you try to bring in the nth term for this, we don't know what that will be in terms of sign. So I bring in the negative 1. And I put the n plus 1 because if you see the way it is fluctuating, right? It is after the first term. So got that over n factorial times 1 times 3 times 5 times 7 times etc. 2n minus 3 over 2 power n x power n and so on. Yeah. Again, you'll have to see, look at more terms to begin to determine the pattern. Okay, so this is what we get. So if I were to, oh, there was a 1. So this is, forget the 1. This is true. This pattern is beginning to come out more explicitly from the second term onwards, right? So I'm going to keep the 1 as it is. And I'm going to take the summation of all these terms and write that as a series. So what we get is, we get summation n 1 to infinity, okay, negative 1 power n plus 1 over n factorial times what we just did here, right? 2n minus 3 over 2 power n x power n. So this is the binomial series we found for square root of 1 plus x. Okay, looks a little complicated because of the square root. You begin to see that it's changing dramatically in the way the series is written. Next we say use the third Maclaurin polynomial P3 of x to estimate square root of 1.5. Use Taylor's theorem to bound the error. Use a graphing utility to compare the graphs. All right, let's begin with P3. P3 of x would be, again, remember that we're trying to use the Maclaurin polynomial, so you want to recall what that is. So to know which one we have to use, I just went back to the question and I forgot to mention the most important information. From the result in part A, use the third order Maclaurin series, okay? So this was actually part B, okay? So I'll say from part A. No wonder I was wondering which one to use. Okay. All right, so P3 of x, let's see. Okay. So that's going to be 1 plus half times x minus 1 over 8 times x squared plus 1 over 16 times x cubed. Yeah. You can see from here. So 2 squared times 2 factorial, right? So 2 squared times 2 here would be 8 x squared. So that's what we have here. Negative, of course, negative 1 over 8 x squared. And the third one is the 3 factorial would be 3 times 2 times 1. So that's basically 3 times 2. And that 3 and the 3 on the top will cancel off. So there'll be a 2 in the bottom. So 2 times the 2 cubed is 2 power 4, which is 16. And that's what we have, 1 over 16x cubed. Okay, so we wanted to find P3. And so we went up to the one we needed for P3. Okay. All right, now let's try to work with the, we need to find the estimate for square root of 1.5. So square root of 1.5, I have to write it as 1 plus x power r, right? So I can think of this as 1 plus 0.5, isn't it? So 1 plus 0.5 power half. We just did a series in part A, right? Part A, we just worked on the series for f of x of the form square root of 1 plus x or power half. So we can call upon that. And in fact, your P3, okay, using P3 approximation, we know that this can be approximated to 1 plus half times where your x is 0.5 minus 1 over 8 times 0.5 squared plus 1 over 16 times 0.5 cubed. Okay. And if you use your calculator, this would approximate to 1.2266. Be careful when you use your calculator on this. All right, the next part says, use Taylor's theorem to bound the error. Okay, so we go back to Taylor's theorem, and if you recall from there, Taylor's theorem on remainder, that one says R3 of 0.5, right, Rn of x. So R3 of 0.5 is f n plus 1, so that is 4. N is 3, so we do 4. That's the fourth derivative of, so f of c over 4 factorial x power n plus 1, and x here is 0.5, so 0.5 power n plus 1, which is 4. Okay. And this is true for some c between 0 and 0.5. Now if you're looking at the formula there, this might help you a little bit. In that formula, we are using x as 0.5, and you know this is Maclaurin, so a has to be 0, right? It's centered at 0. So if you're using the formula, that is what we did with the a and with the x and the a. All right. So f4 of x is negative 15 over 2 power 4 times 1 plus x power 7 over 2. Yeah. The fourth root of x. So you know that, how do we get the f fourth? By the way, this is missing, it's crucial. I'll give you a quick side explanation. You know your f of x is 1 plus x power half. Take the fourth derivative of this one, that's all. So the first one would be half 1 plus x. Half minus 1 is negative half. F double prime of x will be half times negative half, so negative 1 over 4. 1 plus x. 1 plus x power, negative half minus 1 will be negative 3 over 2. The triple one would be negative negative, so positive 3 over 4 times 2, 8, 1 plus x power negative 3 over 2 minus 1 would be negative 5 over 2. And f fourth of x would be negative 15 over 10 to 16. 1 plus x power negative 5 over 2 minus 1 is negative 7 over 2. And you can relate that right away here. It's negative 15 over 2 power 14. 2 power 14 is 16. And the negative 7 over 2 on the top is brought down to the denominator with a positive power. So we know that this is true. Okay. And then we go for the maximum value, because that's how we need this to find the maximum value. So go ahead and find the maximum value of absolute value of f4 of x on the interval, the interval is 0 to 0.5, and see where it occurs. Okay. All right, we've done this previously. To find the maximum value on this interval, we try to see the endpoints and see where it gives us the maximum. You're looking at the absolute value, so we're only choosing the positive part. So even though your the fourth derivative of f, it came out to be negative, we're choosing only the positive because of the absolute value. I'll just give you the quick test, or how we know if it's a maximum value or not. So go to the fourth derivative of x, and in the place of x plug in 0, these endpoints, right? 0 or 0.5. So I'm going to try both. And remember, I'm taking only the positive because of the absolute value, right? So it's going to be 15 over 16. And 1 plus 0 power negative 7 over 2, that is still going to be 1. And see what 15 over 16 is in your calculator. It comes out to be 0.9375. Then try the other value for 0.5. That's 15 over 16. Again, remember, I'm keeping only the positive. 1 plus 0.5. Where are we? Power negative 7 over 2. Compute that. Okay. So you have 0.9375 times 1.5 power negative 7 over 2, right? That comes out to be 0.22680. So clearly this is the higher number, and therefore the maximum occurs there. So we come here and say maximum value occurs at x equals 0. Therefore, we are now confident to go ahead and find the bound, the error bound. So R3 of 0.5 is less than or equal to this value that we just did. So I'm going to put it here, but we just computed it already. 2 power 4, 1 plus 0 power 7 over 2. Do you remember that the absolute value is meaningful only where the x is? So 0.5 minus 0 power 4. Yeah. This again comes from the formula, so please go back and reference it. So that's less than or equal to 15 over 2 power 4 times 4 factorial times 0.5 power 4. Do all the computation. That is approximately 0.00244, meaning less than or equal to, right? And for this, you can go back and check the graph. I will leave that part here for you. Go into Desmos, and because it said if I use a graphing utility to go back and check the graphs. So compare f and compare P3, so that you know, near x equals 0, of course, for the Maclaurin series, and see how they appear. Okay. In fact, the P3, sorry, where are we? P3 is a cubic function, so it is going to be a cubic style function. And your f of x is a square root function, right? And so that, you know how the square root function works. And this function, the two functions actually, cross each other at 1, and that's where they, of course, meet. Okay, so go ahead and test this on your graphing calculator. I want to put up a table that helps you to see the function. It's a collection of, we're not going into the derivatives in detail, but it's a collection of all the functions, their corresponding Maclaurin series, and the interval of convergence. What we've done so far, and maybe a couple of them that we've not seen before. Like for instance, we haven't seen any inverse trig functions and all that. So I'll just put that up right now. So here's the table, and I will let you go over it. For instance, we did the sine x, we didn't do the cosine x, but if you proceeded in a similar fashion, you would get cosine x to have the 2n instead of the 2n plus 1 that we had for sine x. We did not go over natural log of 1 plus x, but we did natural log of x, if I'm right. And we also didn't go over tan inverse of x. And so we have these generalizations for us to use if you come across these problems. If you need more time to look at these ones, of course, feel free to pause the video and take notes. Again, you will need these things for the next course, so it's a good idea to take notes right away. Okay, let's go to the problem here. It says, find the Maclaurin series quite a mess there. It's f of x equals cosine square root of x. So we come back here and we quickly see the connection here. It's cosine x is this. Wherever x occurs, you now have a square root of x. So let's go ahead and remember that. Summation n 0 to infinity. You have negative 1 power n. You have x power 2n, but instead of x, you now have square root of x power 2n over 2n factorial. Let's expand this. So rewrite the square root as a power half. Negative 1 power n. And multiply the powers. So what happens here is this 2 and this 2 will cancel each other, right, when you multiply the powers, and that gives us x power n over 2n factorial. Okay, so if you were to expand this, you get 1 minus x over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial, and so on. The series converges to cosine square root of x for all x. Right? That's what we learned here, and so it. When we say for all x, of course, we want to make sure that it's in the domain of cosine square root of x, right? And so we will make a note of that as well. In the domain of, for all x, in the domain of cosine square root of x. That is, it's for all x that is greater than or equal to 0, right? Because you can have square root of 0 and cosine 0 is good, right? You can't have a negative radicand. So even though cosine can have a negative angle, you can't have a negative radicand, therefore the x has limitations, restrictions. Okay? So we got that. Then we go to B, which is same thing. Find the Maclaurin series for f of x equals your favorite, sinh x. It's been a long time since we had fun with sinh. Well, this had to be the, what do I say, the crowning glory, the last problem of our lecture had to be sinh, right? Okay. recall what sinh x was. Sinh x is e power x minus e power negative x over 2. Now if you go back to our table, so we have e power x and you have this function. So when you have e power negative x, you have to replace your x's with a negative x. We have two e's here because of the sinh formula. So we have, I'll just say using nth term, we have x power n over n factorial. I'm not using the summation, just the nth term, just for us to see. Minus negative x, because this is e power negative x, power n over n factorial, all over 2. Okay, the over 2 is really not a big deal here for us. What is really important is to understand what happens to this term, when you start expanding them. Okay, now what we see is if your n is even, right? If your n is even, then this minus will go away, isn't it? If n is even. So you have x power n over n factorial minus x power n over n factorial. So you'll have a 0 on the top. Doesn't matter, there's 2 in the bottom. So just focusing on the nth term, that will make, if n is even, these two will cancel each other. If n is odd, then you'll have the negative coming out of this, making this a positive, negative and the negative, because the negative raised to an odd power will return a negative. That negative will combine with this negative outside to give us a positive. So then you'll have 2 times of this x power n over n factorial. So let me note that down, this observation that we've made. When n is even, the nth term is 0 because they cancel each other. When n is odd, you have 2x power n over n factorial. Right? I hope I made that point clear, but let me just, when I have a hunch, it's better for me to explain it. So x power n over n factorial minus x power n over n factorial, okay, when n is even, which is 0 over n factorial, or simply 0, right? Now when it's odd, negative x power n, this negative comes out. So then when you have x power n over n factorial minus negative x power n over n factorial, when n is odd, what happens is this x power n over n factorial minus, and then there is a minus x power n over n factorial. And then these two will combine, okay? That is how you get the x power n over n factorial plus x power n over n factorial, giving us 2x power n over n factorial. Okay, that's a side explanation for you. Well, we need some drama for the last lecture, isn't it? So let's enjoy it. Okay, Maclaurin series for sinh x, we see, can only have odd terms, right? Because even terms would be all cancelled off. So has only odd order terms and is given by summation n 0 to infinity x power 2n plus 1 over 2n plus 1 factorial. Okay. Because of the odd power, you have the plus 1, right, to skip the even positions. By the way, you had the 2x power n over n factorial, isn't it? So let me make a quick explanation on that. You do have this 2 here. So there was a 2, and then you had this other 2 over. With that, we come to the end of this lecture. Thank you, class.